Thank you all for attending this presentation by Dr. Amanda Hughes. The title of her talk tonight is Structural Modeling for Reducing Uncertainty in Geologic Interpretations. Before I introduce Amanda, I just want to point out that John Spencer, formerly of the Arizona Geological Survey and now a research associate at the University of Arizona, will be presenting Tuesday, the 2nd of November, Cenozoic Tectonic Extension in the Mojave and Sonoran Desert region. So be sure to come out for that one, invite people to come. We're hoping for a really big crowd. John's been doing this for a long time and knows a lot. But so does Amanda. Okay. Amanda Hughes is an assistant professor of practice in the Department of Geosciences at the University of Arizona. She holds a bachelor's degree in geology from Washington and Lee University and master's and PhD degrees in earth and planetary sciences from Harvard University. She worked in energy exploration and research and development for Chevron Energy Technology Company from 2012 to 2016. She now teaches courses at the University of Arizona in physical geology, structural geology, active tectonics, exploration seismology, and advanced structural geology methods. And she co-teaches professional courses on structural geology for mine geologists and structural geology for geotechnical professionals. Her research is focused on understanding the growth of geologic structures through integrated observations, field geology, active tectonics, seismology, geophysics, and rock mechanics, and a variety of modeling approaches. She's interested in developing and testing new quantitative approaches to observing and modeling geologic structures and applying these methods to geologic problems in energy and mineral exploration, seismic hazard assessment, and regional tectonics. Before I hand it off to Amanda, I do want to thank Freeport and McMullen for sponsoring this meeting tonight. We have a representative of theirs right here in Aaron Conley. Two of you are very good. Three of you, very good. Four. And I'm talking about Freeport. What's wrong with that picture? Okay, Amanda, it's all yours.
Great. Thank you, Mike. And I'm happy to be the appetizer for John. I'm glad there's more structural geology coming up soon. So thanks so much for having me. And today I'm going to talk about how we can integrate observations of geologic structures from the field, from seismic reflection data, and from mechanical models that help inform how we think structures should form, and use that to guide our geologic interpretations of the subsurface so that we can make better constrained, less uncertain interpretations. So I'm going to start talking about geologic structures. Why do we want to study them? This will be obvious to many of you, but just highlighting some of the reasons. What do we think we know about their geometries? What are some different types of ways that we can model them? Turns out there's lots of different ways, so what are some of the best use cases for each of them? And I'll show you some examples of each of those that we're working on in our group. And so I'd like to leave the talk at the end by saying that if we can work toward a physics-based framework that can reconcile our observations of natural structures and what we think they physically could do based on rock mechanics, then we can be more confident in our interpretations of the subsurface, and we can use that for lots of helpful applications. So this is a typical problem that we would face as geologists. And this is an example from the Foreland-Fold Thrust Belt onshore Taiwan. In our cross-section here, let's see, do I have a pointer? Okay, no. Okay, sorry. So we can see that in our cross-section here, we have typical distribution of data. We have surface geology, surface structural, dip information and contacts. We might have some limited subsurface data with contacts and dips. And in all of these cases, from this limited subsurface information, we have to extrapolate out from that data and compose a complete picture of the subsurface. And so you might make a cross-section like this one that honors all of the available data. It matches all the dips, it matches all of the contacts. And somebody else might make this cross-section that also honors all of the available data. And so which one of those is right? They're pretty different, right? These two are quite different. And so are we just left to argue about it forever and never reach a conclusion? Well, I'm very conflict averse, so that would not suit me very well at all. And so I would argue that we want to develop these structural tools so that we can limit the otherwise infinite different ways that we can honor the available subsurface data and try to narrow down the range of what the possible geometries could be in the subsurface. So this is an example that for instance, not only honors all of the available contact information, but also does some basic first-order structural things like have consistent amounts of slip along faults and preserve layer thickness where available, which is something we might want to do in fold and thrust belts because that's something that we observe in these types of settings. And so based on these things, we can use general structural constraints like those, area balancing, kinematic modeling, and mechanical modeling to try to constrain our subsurface interpretations. And by doing this, this leaves us with the ability to make some sensible, permissible, and quantitative predictions in areas where our data is poor or ambiguous. However, like I said, there are a lot of different types of modeling approaches. Each of them have their own benefits and disadvantages, so that's what I'm going to talk about today. So first off, why would we want to model structures? This beautiful example of cross-sections of the severe fold and thrust belt is a nice example that if we have typical surface data, structural contacts, stratigraphic contacts, dip information, and some limited subsurface data, you would need to make a lot of model-based interpretations in order to figure out the geometry of a fold and thrust belt. But based on that, we can make a lot of interesting interpretations trying to understand fundamentally what's the form of a fold and thrust belt, what types of structures exist in them, and how do they accommodate shortening in the Earth's crust. I should say at this point, I'm going to show almost exclusively examples in shortening just for the sake of time, but I could have talked about normal faults too, and hopefully I can come back and talk about normal faults another time. So other than just fundamentally understanding how structures shorten and deform the Earth's crust, just because it's a fundamentally interesting thing, it's also incredibly useful for a lot of reasons. So for example, in petroleum systems, a lot of times surface information is not available. This is a case where you can see in the shallow part of the subsurface that there is not any, oh, that's better. So you can see there's no expression of the anticline that's present at depth at the surface. Those layers up there are flat, but the anticline is present down here. And even in this case where we have seismic reflection data, we can see that there are portions of that where the data is unambiguous and we can see reflectors, but there's other places like over here where that's much more difficult to see. And so we still need to have model-based ways of going from the places where we have good data and trying to understand what the geometry could possibly be in those other areas. This is important not only for characterizing the geometry of traps in petroleum systems, but also for figuring out the timing and magnitude of shortening, distribution of strain in the subsurface, which has implications for how fluids will flow through those systems. That, of course, petroleum fluids are one type of fluid that flows in the subsurface, but any other fluid needs the same kinds of constraints. So the same types of structural modeling approaches are necessary for other energy systems, like geothermal systems, for example. Now again, if we have fluids flowing through the crust, some of those fluids can bear mineralizing fluids. And in a case like this, we can see that there's primary structural controls on the grade of mineralization in many mineralizing systems. So this is an example, this is a very nice cross-section from David Rees of the gold mineralization in the Carlin Trend in Nevada. And what we can see here, the geometry of the faults and folds are expressed in the cross-section, and in red hatched in here, that's the location of gold mineralization. So we can see that the gold mineralization is strongly correlated with the geometry of the structures, and the reason for that is that the structures are creating the fracturing and permeability pathways by which those gold mineralizing fluids are traveling through this structural system. So if we have better ways of predicting the geometry of these structures based on the limited data information we have the, of course, the exposures in the open pit, and then in gray lines here are the drill hole traces. But if we have structural modeling approaches we can use, we can better predict the geometry of the faults in the subsurface, which can guide mineral exploration. And of course, the last thing we may want to do here in terms of characterizing fault geometries is seismic hazard assessment. This is an example from the Santa Fe Springs anticline in the Los Angeles Basin. At the surface here, you can again see that there's very little expression of these folded layers. There's a little tiny fold right there, which if you look at the picture here, you can see you can drive right over that fold. But that fold has been generated due to slip, due to progressive earthquakes, approximately magnitude 6 to 7 earthquakes on the Puente Hills thrust fault system. And we can therefore, if we have structural modeling approaches, that we can relate the folding and uplift of these rock layers to the geometry and amount of slip on the underlying fault, we can better assess the seismic hazard associated with these structures. So I think we're feeling very motivated to characterize first-order geological structures, but there are other types of structures we would want to predict as well. One of those that's quite important are fractures and joints. And if we look at sets of regional fractures and joints, this is an example from the Appalachians. We can see, there we go. We can see that the orientation of the joints varies quite systematically at the regional scale. And so therefore, because that varies systematically, it must relate to things that we have a physical meaning and therefore can model. These orientations have been related to the state of paleostress, and therefore there are other types of structural models that we can use to try to predict their orientations and distributions in the subsurface too. And fractures, of course, are important conduits for lots of those subsurface fluids that I mentioned before. So again, we would want to predict them for the purposes of mineral exploration, geothermal, petroleum, hydrologic, and subsurface storage applications. So how do we develop these structural models, and what are they based on? They're primarily based on empirical observations, looking out in the field at what structures really look like. In the case of fold and thrust belts, we look at structures like those pictured over here in the Canadian Rockies and observe things about their geometry and then develop models that conform to those observations. We also make observations from seismic reflection data and deformation of active structures. And then when it comes to understanding the mechanics, we want to honor things like laboratory rock strength tests, field observations of strain, and things from active tectonics that constrain how strong the crust must be. So a useful structural model would be consistent with both these empirical observations and what we think must be required by deformation of realistic materials. That would make a model plausible and possible. So structural models are broken down into three main categories. There are geometric models that describe the shape of the structure that must be present. Things like this one here, where we would describe the orientation of this triangle, its lengths, its point locations. That would be a geometric description. If we wanted to understand how the structure attained that geometry over time, that would be described by a path of deformations over time, which would be a deformation field, and that would describe a kinematic model. And if we instead wanted to take this deformation and understand what are the physical processes, the stresses, and the rock strength properties that give rise to that change in shape, that would require a mechanical model. So we have all these different types of things that we can bring to bear on describing structures. Let's start with geometric models, because this is likely the most commonly applied one. And the most commonly applied one is an interpolation. So an interpolation is simply taking the sparse data that we have from a geological context. Maybe we have surface contacts and we have penetrations from core, like we see over here. We have two formations that are outcropping and have been sampled by a set of core. And what you can do is extrapolate from those locations a three-dimensional representation of what you think the geometry is. The simplest of those are fairly isotropic, and it helps you in first order to find outliers and find things that are permissible or impermissible about your interpretation along strike. But there are a lot of disadvantages to only using interpolation. First of all, it's highly sensitive to the spatial data that underlies it. So if you take that same set of data, this is an example from Reed and Cowan, 2023, and you sample that same synthetic structural geometry, in that case a fold, with a different set of well penetrations, you get a dramatically different assumed interpretation of the geometry. So absent any other structural interpretation and structural basis for making that interpolation, it's a fairly non-unique solution that can lead you to a very different understanding of what the geometry of the subsurface might be like. And again, these are different samplings and different assumptions in the interpolation that lead to those dramatically different outcomes. Okay, so if we want to take our interpolation and add some more structural constraints to it, The types that we would choose to use would vary as a function of what type of problem we're trying to address. And so I want to start out with low strain problems first. So low strain problems, because there's not a lot of deformation involved, we don't have to be too worried about the path. So we can cancel out kinematic parts, and we just want to describe the geometry and the mechanics of those systems. So one of the most useful ways of approximating low strain problems is through an elastic mechanical approximation, like a boundary element model or finite element model. This is a boundary element model. This is a map view showing what it would look like if there was a fault under a far-field regional state of stress. And if the fault is perturbing the local state of stress due to a very small amount of displacement, you can approximate the geometry of what any other additional small offset structure that forms within that stress field would have. And so that's what they've done in this example. And I just mentioned boundary element models are the simplest type of version of this type of low strain mechanical modeling. Finite element models are a little bit more complex. They take more time, and you can incorporate more heterogeneity, like layered materials, into them. But they have a lot of complicating factors, such as challenges associated with meshing and challenges with higher strain conditions. So I'll stick with the boundary element models for now. But if you're in a situation where the perturbation to the stress field is significantly modifying the regional stresses, and then the amount of strain that actually happens is fairly small, this can be a really useful tool for predicting structural geometries throughout the rock mass. And a great example of that, one of the best described ones, is in the Spanish Peaks in Colorado, where there was an intrusive volcanic complex with a set of dikes emanating from it. And these occurred in a regional stress field, and so you can see that very proximal to the volcanic center, there's radial dikes, but that they rotate in their orientation as a function of how the relative contributions of the local stress perturbation of the volcanics relative to the regional stresses. So you can see at the bottom here is a boundary element model that's best fit to these orientations, and you can see that this elastic boundary element dislocation does a really good job of predicting those dike orientations. So this is a really helpful type of modeling approach for that type of a problem. We're extending that type of approach to understanding how strain is distributed around salt structures up in the Paradox Basin. So the Paradox Basin sits up in the Four Corners region, and we're working on this portion up here in central Utah. In Salt Valley, but this area is characterized by a series of salt walls. A perspective view of our 3D model is shown here. This 3D model does use geometric interpolation, but it's also based on a series of restored and balanced cross-sections that allow us to build out this nice 3D model. And then we can place that in a stress field to try to understand how any fractures or joints that form adjacent to the salt structures might be oriented. And this is just a slice through. We've taken this model, and put it under a regional state of stress that represents the modern state of stress. And this is a little slice through that model. So what we can see here is the top of salt is shown in purple. This is the contact between the salt itself, which sits underneath that purple, and the adjacent sediments, which are represented by the layers that abut onto that purple salt. And then if we look at one particular layer and see, based on this elastic dislocation model, what stress field orientations would seem to have to be, because the salt itself perturbs the stress field, because salt is inherently very weak, can't sustain shear stresses, so it really modifies the stress field. We can see that there's a significant rotation in the principal strain axes in there. So if you just look at the green axes in there, you can see that they rotate really substantially in their orientations throughout just this limited part of the model. This gives us a model-based prediction that we can compare to places where we do see data. And this is the full map view of this model. What's shown on here, this is now a little bit reoriented, where north is now pointed in this direction. I just oriented the model parallel to the salt walls now. We can see the salt walls and the welds where the salt isn't present. And we can see on here mapped our The black lines are the predictions of orientations of fractures that we should expect to see that have a dip of greater than 60 degrees, which means we would be able to see them in satellite data. So if we take this little area down here, down on the southern portion of Spanish Valley, just south of Moab, Utah, you can see that the model is predicting a significant rotation in the orientation of fractures that would form under the stress field predicted by this model. And when we look at the satellite data, we can see that same rotation of the fractures. Now, it turns out the reason that that's occurring is because the Spanish Valley salt wall is plunging towards the south. The salt is getting deeper. And so when you apply that far field stress, you get that rotation towards the plunge end of the salt. So we're able to reproduce that in the model. If we look over here, this is an area where the salt is welded out. That means that deformation of the salt has completely evacuated the salt at that location. And you can see that we predict vertical, subvertical fractures in that location. And again, we're reproducing what's observed in the satellite data. So we see that's what's predicted in here, and that's what's observed in the satellite data. So again, it looks like our model under the modern day state of stress is able to capture those orientation variations. Therefore, we can interpret that, we've broadly got the geometry of our problem correct. When we apply the far field stresses associated with the modern day stress field, we're able to match these particular sets of regional fracture sets, so we can assume these regional fracture sets formed under kind of the modern day state of stress. That's helpful if we were, for example, relying on these fractures for flowing fluids for mineralization, right? We would say these fractures weren't here during the Laramide or during the Permian or something like that. These fractures formed under the modern state of stress. If we look at another area of Salt Valley, up towards the northern part of Salt Valley, north of Moab, we see other sets of fractures that couldn't possibly have formed under the modern day state of stress. So this was some work done by recently graduated PhD student Lauren Rear, who I think you all have heard from before. And so what you can see here is that instead of seeing those big regional exhumation-related joints, we see sets of conjugate shear fractures in the field, and in addition to the regional joints. But what we notice about them is that as you move with distance away from the salt, which is going from east to west, we're getting further away from the salt right here, and this dissolution-related fault, and then we go further into the sediments, in this case sandstones adjacent to the salt. You can see that we go from a state of stress where sigma 1, the maximum compressive stress, is vertical, right adjacent to the salt, and sigma 2 is horizontal. And then as we go further and further away from the salt sediment interface, we go to a strike slip state of stress where sigma 2 is the vertical stress and sigma 1 is a horizontal stress. So if the far field stress, sigma 1, is horizontal, that can't happen under the modern day state of stress, which is extensional in the paradox basin. So this must have happened under a different far field state of stress. If we apply what we think the regional far field state of stress was during the Laramide to this model, we're able to reproduce that really unusual local state of stress perturbation. So this is the salt, top of salt. We have the salt wall. Now we're oriented kind of looking along strike on the salt wall. And we're looking at the top of the Moab tongue member here, which is the formation on which we're observing those sets of conjugate shear fractures. And what we can see in this case is that if we apply even a far field compressional stress, which is what would have happened during the Laramide, we get sigma 1 being vertical over the top of the salt, which is the opposite of what you would think for shortening, right? But that just shows how substantially salt can modify the state of stress. And then as we move away from the salt sediment interface, we see that we're returning to a horizontal state of sigma 1 into a strike slip stress regime. So one of the valuable things about applying this type of model in a low strain environment like the formation of shear fractures or joints is that it gives you a basis on which you can test ideas like paleo stress conditions and timing of when different types of structures could have formed. All right, but what happens if we move into a higher strain type of environment? So if we need to characterize higher amounts of strain, elastic approximations aren't going to be a very accurate approximation of the strain anymore, because as you all know, when you're accruing big amounts of strain, that's anelastic permanent strain, and the pattern of that is just not well represented by an elastic approximation. So if we're going to do that, we not only have to describe the geometry and mechanics, but we need to understand the full path, the geometry, and how the geometry evolves over time. So this would be one of those things that instead of simply doing an interpolation like we would have before, we could apply some of these first-order structural assumptions to further narrow down the geometry in these higher strain situations. Okay, so the first-order kinds of things we would want to do are simple things, right? Things that we all know from our structure class, like area balancing. Area balancing is just simply taking the deformed state and going back to the undeformed state, and if the cross-sectional area before and after deformation, as indicated by the line lengths being equal, is the same, then we would call that cross-section area balanced. And that's a good first-order constraint. We, of course, know situations like formation of cleavage or tectonic compaction where that's not a great second-order assumption, but first-order, we don't want to create or destroy any material in the deformation process. And so this would be our first-order kind of structural assumptions. What would a kinematic model be? A kinematic model is simply taking the deformed state and the restored state are both area balanced, but the additional constraint added by a kinematic model is saying every single path along a realistic path between the undeformed and deformed state must also be area balanced, which is a narrower range of permissible solutions. So that's what makes something kinematic. The form of these kinematic solutions is that they are still based on naturally valid principles and kind of observed mechanisms of deformation. So for example, in shortening, like I said before, we're either going to preserve layer thickness, because that's what we actually observe in natural fold and thrust belts, or if we're going to vary the thickness of layers, we vary it in very specific places that we know we see them in real structures, like forelimbs, for example. So these kinematic models have been applied for a long time, and there's kind of two different schools in structural geology. There's kind of kinematic modelers and mechanical modelers. And the kinematic models, again, are just describing the geometry of the structures that are present. They're based on these first-order assumptions. They don't require a detailed knowledge of the rock strengths and properties. They're relatively easy to apply, particularly for types of simpler structures. But they have some disadvantages, too. They don't incorporate the mechanical properties. So if you're in a situation where the relative rock strength is really dictating the style of structures that are forming, then you're not going to be able to capture that very well with a kinematic model. It's limited to relatively simple cases, so in more complicated cases, you often have to manually construct these models, which can make application difficult and limits who would want to do it, right? Mechanical models, on the other hand, do incorporate our understanding of rock properties, but in high-strain cases, the structures that form are simply emergent, so you can't really model any particular structure you want to. Whatever happens, happens in a mechanical model, right? And so you might say, I want to model this particular structure, but that might not be what comes out of your model. So one of the things that we've been working on is to try to take the insights from mechanical modeling about what types of structures tend to form in different circumstances and use those to refine the kinematic modeling approaches that we use. So let's start with the mechanical models. There's two main classes of mechanical models. There are analog mechanical models, sandbox models, which many of you are probably familiar with. There's a really nice example of a fold and thrust belt analog model by new U of A faculty Johnny Wu and Ken McClay in 2011. And then we have a numerical model, which is basically just a numerical sandbox, in this case, a discrete element model from one of my papers, where you're basically simulating the same thing numerically, and there are some advantages and disadvantages to each of those. One of the advantages is highlighted here in the numerical models, which is that you can track stress and strain evolution throughout the evolution of the model. As you can imagine, the disadvantage to a numerical model is you're limited by computational power and time, right? So analog models, you will have much more ability to model higher resolution things and three-dimensional things, whereas numerical models, you have much more granularity, no pun intended, in terms of the stresses and strains that you're able to extract from that type of model. So the numerical models, there's many different types of them. There are discrete element models like the one I'm showing here. There are also more advanced finite element models like critical state or extended finite element models or particle and cell. I don't have time to talk about those, so I'm just going to talk about DEM. One of the disadvantages to using mechanical models is that they incorporate rock properties. That's also its advantage, right? But the challenge to that is that's assuming you know the rock strengths at the spatial and temporal scales at the time that those structures form, which we don't always know. We know in a rock laboratory sense what those might be, but extrapolating them out to the scale of a fold and thrust belt that deforms over 1 million years is a logical assumption. So discrete element modeling, you're basically approximating the rock mass by a series of spheres that interact with each other at the microscopic scale, and then using that to approximate the bulk properties of the rocks. So you can see an example here by Julie Morgan that shows that you can track stresses and strains and displacement gradients and see how the deformation evolves in these types of structures. The advantage to using this type of approach to understanding structures is that you can model emergent deformation and see how important different aspects of the rock strength are. You can also model mechanical heterogeneity relatively easily, change rock strengths and layer thicknesses and things like that. So it's very good for hypothesis testing. We can use these discrete element models to better test the limits of the existing kinematic theories that we're going to look at next. And so that's what I primarily use them for in our group. And the advantage to doing that is that then gives us a physics-based basis on which to make modifications to our kinematic approaches. I'll just show a quick example here. Again, fold and thrust belts. We know fold and thrust belts are comprised of a variety of different structural styles. There are fault bend folds, where folds form as rocks are displaced over bends and faults. There are fault propagation folds, where folds form as faults are propagating up through a sedimentary section. And then there are lots of other types of structures like detachment folds, wedges, duplexes, all these different types of things. And in some cases, like the severe fold and thrust belt down here, we can see we have a whole variety of different types. There are fault bend folds, fault propagation folds, duplexes, like that one right there, and imbricate stacks, all kinds of different structures mixed together. On the other hand, some other fold and thrust belts, like the Mexican ridges in the Gulf of Mexico, seems to be dominated by a single structural style. So we want to know mechanically why this is happening so that can inform how we make interpretations in those different types of settings, how that relates to rock properties, for example. I won't go through all of this, just to say that the interparticle properties of our discrete element model ultimately dictate things about the strength of the rock mass. So things like Young's modulus, how strain weakening the rocks are, what the peak strength is, the residual strength of the rocks. And fundamentally, we can apply variations of that to see how important they are in terms of what kind of structures develop. So we just set up a numerical sandbox like this and shorten it. And you can see that if you make those variations in rock properties, you get different structural styles that emerge. So sometimes, like down here, you have low peak strength but low strain weakening, which means there's not a lot of preference for localizing deformation, and you get big, broad, rounded folds. On the other end of the spectrum, if you have relatively high peak strength but high strain weakening, you tend to have much more localization and formation of faults. And if you have other combinations of properties, you can see sometimes we form a single structure, and sometimes we see the importance of detaching on those weak interbeds and the formation of lots of second-order structures. So this kind of mechanically based model you can set up specific to a particular mechanical situation. We're working on an application right now where we have interbedded salts and shales, and we just prescribe those exact thicknesses, and we can see what the effect is in terms of the style of deformation that's occurring in those settings. It's just a very good tool for testing these hypotheses and then trying to relate those aspects of layer thickness and rock strength and rock properties to the geometries of the structures that actually emerge under those circumstances. So finally, that brings us to kinematic models. Now, the advantage to using kinematic models is that they are predictive. So they provide angular predictive relationships between the shape of folds and the shape of faults. This is an example of one, which is fault bend folding, that I'm going to build on here in the last bit of the talk. So we have a fault bend fold where the fault has bends in it. As the rocks displace over those bends, they create folds. And the geometry of those folds are directly geometrically related to the geometry of the fault on which the displacement is occurring. So these analytical solutions for these angular relationships are what comprise the kinematic model for fault bend folding. So I mentioned it's kinematic, which is to say that if I take it from the deformed state here to the undeformed state, all of those models area balance, right? So that's what makes it a kinematic model. It's that every step along its path is a permissible solution. So as I mentioned before, these are easy to construct. They're based on first order assumptions. But the disadvantage is a couple of things: not incorporating mechanical properties, limited to simple cases for which there is an analytical solution that's been derived for kinematic modeling. And in other cases, the application can be quite time consuming. One of the other limitations that lots of people will cite about kinematic models is that they're very angular, right? And when you go out in the field, you say, my structures aren't angular like this, right? But it turns out that's not a fundamental limitation of kinematic models. And that can be mitigated by developing new methods. This is an example of just that type of structure, right? So this is a seismic reflection profile from the offshore Niger Delta. And we can see the fault is very nicely illuminated with a fault plane reflector right through there. And we can see a fold overlying that fault. But rather than being a quite angular fold, it's a nice, broad, rounded fold. And so you might look at a structure even as simple as this and say, you can't model this with kinematic models, right? It doesn't look angular, but you can. I wouldn't show you if I didn't think you could. So the existing kinematic models we've already covered. They have advantages and disadvantages. The advantage is that they are widely applied to these specific structures and quite predictive, but the disadvantage is that they're limited to simple cases and defined styles. We have a velocity field implementation that mitigates some of these challenges and allows you to do lots of different other things. That's the basis of a paper that we just published in 2021. And so the details of that are in there, and the modeling code is free and publicly available, so shoot me an email if you want a copy, if you want to play with it. Please do. And you can use it for your stuff. So the kinematic solution, in the first place, has this type of form. And basically, this is not our solution. This is the pre-existing solution of the analytical fault bend folding equations that was derived by John Suppy. And what these are based on is, again, these fundamental first-order structural constraints, which is preservation of the area. So if you have a fault that changes its shape, like the fault does here, and you have this triangle of rock that displaces up here, that green triangle before and after deformation has to have the same area. And if we're going to preserve layer thickness, then the length of that blue line L and L prime has to be the same before and after deformation. So you have four variables, basically. Oop, there we go. We have these angular relationships between the fault and the folded layers before and after the bend. We have two constraints, the area balance constraint and the fault geometry and the line length constraint. So there's two analytical equations that prescribe the angular relationships between those features. All we did in our paper is that we took those angular relationships, and instead of analytically solving them, we recast them as a velocity field. And so this velocity field simply prescribes that for these different portions of the rock that are on different sides of folded layers, which is dictated by the geometry of the fault in here, we've then recast the fault bend folding equations in terms of these displacements both in the horizontal and the vertical direction prescribed by U1 and 2 and B1 and B2. So that is simply solving these equations at every time step as you're moving material through these bends, allows you to refold things, change velocity boundary orientations over time. And now because we have a velocity field solution, We can do all kinds of other things with it too. So here we come back to our example from the Niger Delta seismic reflection data, and we can model this. Now, because we have this nice big rounded fold, it's going to require that we have a nicely rounded thrust fault to accommodate that. So if we have a fault like this, as we move material across those multiple bends, it's refolding and refolding over time, and that's what gives rise to this nice broad fold. We can see the green layers are pre-growth, which are sediments that were there prior to displacement on the fault. The blue layers are sediments that were deposited while that structure was growing. So if I go back in time, the green layers were there before any displacement on the fault. And then we start to add these blue sediments on top. You can see that they're on-lapping onto topography on the structure. And that actually is manifest, if we could zoom in on there, we can see those specific onlaps in the growth strata. That tells us we're getting the kinematic evolution of that structure correct, and it gives us some constraints on the relative uplift to sedimentation rate during the growth section. So there's all kinds of double checks that we can do in here and additional information we can pull out of it. But ultimately, I just want to show fault bend folding. If you recast it in this way, you can model it really simply. It takes like 5 seconds to run this model. And so because we have this computer model, now you can test lots of different models and you don't have to manually construct them anymore, which was like very time prohibitive, I would say, in terms of trying to model these types of structures. We can model lots of other types of structures too. We can model imbricate. So now we have a break forward structure that's refolding the fold and fault that was already there. Because we're recalculating the axial surface orientations at every time step, we're preserving layer thickness in that back limb, unlike some other approaches that are out there. And because we're able to do that, if we come again to another seismic reflection example here from the Niger Delta, we have one fault that comes up through here. We have another fault down here that refolds. So down here, what's pointed to by 1 has been folded once over this fault in this break forward imbricate sequence. And this fault up here has been folded once due to displacement on that fault and twice by refolding. And so we can model this structure using our approach, and this is the resulting model that we get. You can see that we're honoring those seismic reflectors that are associated with that fold. On this one, we're matching the cutoffs that are indicating where the fault is up here. We're matching all the cutoffs in the seismic reflection in here that's matching that fault geometry, and we're matching the geometry of that refolded section really well. If we didn't recalculate those axial surfaces, that's the solution we would get. And so we can see that our solution that we've worked out does match that back limb much better. I'll go back to the other one. So you can see we're preserving layer thickness in there and matching those geometries much better. Of course, this is an example where the seismic reflection quality is so good, of course we can see that it matches well. But that gives us confidence that if we went to a place where we had way less data constraints, we should feel confident using this type of approach to interpret in those sections too. Okay. We can do other things. Again, because we have a velocity field-based solution to this kinematic model, we can incorporate other field-based things like erosion. So as we can see, as we develop immersion topography in this case, rather than just lopping erosion off the top, we have a diffusion-based erosion built into this, so we can actually see how topography might evolve in this model over time. And that leads to some interesting and maybe counterintuitive outcomes, right? So the crest of the anticline that developed there is not the high point in topography. The high point in topography sits back here because that's what's over the thrust ramp. That's what's actively moving material up. So the stuff that's in the crest has now been advected and is now moving over that upper detachment. It's no longer the high point in topography as erosion continues to evolve. So because we're able to model that type of thing, we can make sense of examples like this one that comes from Don Medvedev. This is from the San Joaquin Valley subsurface example that's constrained by well data. And you can see that there's this fault and fold geometry that he's interpreted, and this really interesting progressive on-lap unconformity geometry seen in here. And that's something we can reproduce in our models. So again, having this different recasting of the kinematic solutions is really helpful. And I don't have time to show all of them, but you can use it to model extension 2 and inversion structures. Here we have our simple fault band fold up here, but here's our inversion structure. Starts out normal and then inverts. We can model breakthrough structures of interesting varieties, imbricates, duplexes, all kinds of things. So we can model the kinematics and honor them and say, if we adhere to the kinematics, this is the velocity field solution. But now that we have this code, we can say, well, maybe we don't want to honor the kinematic modeling solutions. Maybe we want to do something different. So this is a nomogram of the kinematic model solutions right here. And if we perfectly honor them in this particular example, we would fall along that line between the red domain and the blue domain. But if we change our axial surface orientations, we would fall into one of those other fields. And in the red areas, we would be imposing a boundary that would cause the layers to thin. If we're down in the blue part of this angular solution space, we would cause those layers to thicken. Well, why would we want to do that? We could do that if we had mechanically a good reason to want to do it, right? So again, we can go back to those mechanically based models and see if we have a good excuse for wanting to do that under certain situations, or are the kinematic models always perfect? I don't know. Let's find out. So you would set up a model where you knew the fault geometry, like you do over here, and you can vary things like the fault dip or the layer strength or the layer spacing and see what happens. So here's an example. The fault's dipping 20 degrees. We get this kind of rounded fold, but this is the kinematic model prediction for that fault geometry, and it's not bad, right? It gets the kinematic the pre-growth layers in there pretty good. The growth layers that are shown in green and yellow and gray in the mechanical model are not quite as well fit. So that might motivate us modifying that kinematic model a little bit to try to match the growth strata a little bit better. So we can approximate that single bend as a couple of distributed bends and move, instead of having a discrete locus of folding, because the rocks have some inherent strength, if we spread that out over an area, we get a much better solution. That solution makes a prediction as to where there would be strain in this model, additional strain. What's shown in here is the layer parallel shear that's predicted by our kinematic model, and you can see that it's predicting that we should have negative layer parallel shear in here, which is shortening. So if we were using this to for example, inform a mineral exploration project, and we were trying to guess where we would have second order shortening structures, the areas highlighted in blue might be a good place to look. If we go to 30-degree fault dip, the kinematic model is not a good approximation, so now we can see we clearly need to modify it by having a more distributed folding geometry. In this case, we would be predicting that we would have extension in those locations. So we might have boudinage or formation of normal faults or fractures, depending on the mechanism and the location that we have of interest. And then if we have a fault dip of like 40 degrees, for example, we're already outside of the kinematic fault band folding solution space, which means there's no way to preserve layer thickness anyway. So what do the rocks want to do? They know they can't predict layer thickness because there is no theoretical solution in this case. But we can see that we can still model it with a strain minimization in our code, and that we can match that geometry that the mechanical models are telling us must be present. And that, again, gives us predictions as to where we should expect extension and shortening to have formed in this model. Of course, we can go back to our mechanical model, and because it was a numerical model, we can see where the strain actually was. And we can see in our model, this is a visualization of distortional strain, and we can see that we're causing lots of distortion that crosses bedding, and therefore is the mechanism by which we're thinning those beds. And so we can kind of reconcile those two things. We can say, we can see that the mechanics is requiring that. We can characterize the kinematics as being consistent with that. And so we can reconcile these two otherwise previously treated as disparate approaches to characterizing these high strain models. This is just a concluding slide that says that I could have given this talk about normal faults. The same kinds of things apply, right? You can do normal faulting, kinematic descriptions. Our modeling program does normal faulting as well. You can generate normal faults in analog and numerical mechanical models, and you can use them to reconcile those as well. So in conclusion, there's a lot of different types of structural models. In low strain cases, things like elastic approximations are really useful in helping to better constrain your structural geometries at depth. In high strain cases, reconciling kinematic and mechanical models to have more accurate representations of the subsurface can again give us better interpretations of their geometries. And then ultimately what you would want to do when working in 3 dimensions is use those mechanically informed kinematic modeling constraints to generate a series of cross sections that you then would use as constraints in your interpolation so that you have the most structurally consistent interpretation possible, and from that you can make lots of decisions with more confidence. So I want to thank my collaborators, particularly Lauren Rear, my recently graduated graduate student, Chris Connors, who we've co-developed the kinematic modeling code along with Stephen Ball, and then Seth Bassetti in particular, where we're working on the elastic dislocation modeling. So, thanks.
Showed, do you have any sort of analogs for out-of-sequence thrusting in any of those that sort of approximate actual drilling or anything going on in the oil and gas industry?
Yeah, so you can generate out-of-sequence thrust both in the mechanical models and you can make them in the kinematic models too. I think there might have been an out-of-sequence thrust in that big slide that I showed a million different structures. Yeah, that one. Yeah, this breakthrough is out of sequence here. So yeah, you can use this to model out of sequence structures. Out of sequence structures in the mechanical models, particularly in fold and thrust belts, tend to form when, anytime the critically tapered wedge needs to keep up with deformation, you get reactivation of structures in the hinterland. But then especially if you have erosion off the top, because then that decreases the surface topography and the wedge has to like reactivate in the hinterland to keep back up. So I could show you some of those examples sometime, but yeah, you can generate those mechanically, but you can also model them kinematically too. Yeah.
Okay, thank you. I have one more question.
Yeah, of course.
For the, I guess, what data is defining the contacts between your strata for your models?
For which model?
I guess it was the DEM that you were showing. You were talking about I think sort of the rheology of each bed that you had, and I was just wondering if there was any data that sort of tractional stresses that you have, because it seems like mechanical stratigraphy is a huge part of all of that. So I didn't know if the contacts between those had anything to play a part in.
Yeah, so the DEMs that I showed here are just really general ones, like the layers are like they're all 100 meters and 10 meters and 100 meters just to see like the bulk effects. But in the case where we're applying it in the Paradox Basin, we have a couple of well logs that are telling us what the relative thicknesses of the layers are, and that's what we apply as our layer thicknesses and strengths from rock mechanics tests to tell us like what should that deformation look like. Okay. In the boundary element model with the salt, our contacts are dictated by some well data. There's about 10,000 wells within the Paradox Basin, so we have those. Some places they're sparse, so we had to build balanced cross sections that constrain that geometry. It's inherently somewhat uncertain because we don't have seismic reflection data there, unfortunately. So that's one of the things we tested, is like how well do we know that geometry, and if we got it wrong, we would not match the stress field variations very well, right? So that's kind of an iterative modeling process.
Gotcha.
Yeah.
Thank you.
Yeah, of course.
Thank you very much for the presentation. I just had a quick question about how useful will this hybrid models, that's the kinematic with mechanical properties, be useful for kind of modeling salt diapers intrusions? Salt diapers would like intrude through the sediments and then have this sediments tightening above them, which is slightly different from like faulting, but how useful would the models be for modeling intrusions?
So you're saying, I missed what kind of data input you mentioned?
Yes, like if we have, let's say, data from well logs and we have some seismic images, like seismic cross sections, how useful would the models be for modeling the salt diaper intrusion?
Oh, how the salt diaper grew in the first place.
Yes.
That would require, you could model that with discrete element modeling. The evolution of the salt diaper itself is a fairly high strain process because the salt itself undergoes a brittle ductile transition at a few hundred meters depth. And so it's like toothpaste under almost any sediment loading. And so the salt itself has a huge amount of strain. You would need a DEM to model. Or there's some groups at UT Austin who are doing really good critical state finite element models of salt evolution. So those models model, for example, if you deposit sediments on top of the salt, how does that salt structure evolve over time? Again, that would be a high strain problem. So you would need that type of approach.
Thank you.
Yeah, of course.
Okay, good evening, excellent talk. You just answered my first question. So the second question is, I was at the University of Austin in Texas visiting a lot of seismic modelers. They had regular conferences. And one thing there at the economic geology department, which is oil mostly, not ore deposit economic geology, they had these wonderful sandbox models in acrylic basins, and they very beautifully modeled salt tectonics in the Gulf of Mexico. Does this kind of work that was mostly done by Martin Jackson and consorts a few years ago, and Mike Rudek was his name?
Yeah, and Tim Dooley.
Does this match what you are doing on the computer?
That's a great question. So none of the ones I showed here are salt tectonics models. You can generate those. In particular, Stuart Hardy has been working on discrete element models of salt evolution. I haven't been doing it in my lab too much, but you can, yeah. And Stuart has had great success reproducing some of those. Like I mentioned, the challenge is that there's such inherent three-dimensionality to the salt structures. Numerically modeling that takes like a month to run that model.
Yeah, it's too wild.
Yeah, so you have to pick your battles very carefully, and I haven't modeled a lot of salt structures, but Stuart has.
Excellent. Thank you very much.
I would love to in the future.
And good luck.
Thank
you.
Thanks. Great. Yeah.